All right, here are the free response questions from the most recent session of the 2012, of the AP Calculus BC, the 2012 sitting of the test. Here's number 1. And we've got a graphing calculator for this one. Temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w. Don't be intimidated by that. That just means you can make any assumptions you need to about derivatives existing. Where Wt is measured in degrees. So here this is the temperature. And T is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time t equals 0. Values of W are at selected times for the first 20 minutes are given in the table above. So you can see the temperature going up. All right, it looks like it was going up more, like in the first... oh no, that's not true. Here it went up like 2.1 degrees, and then in the last 5 minutes it went up by, what, 3.1 degrees? So I guess we'll see. We'll probably be finding some slopes. Use the data in the table to estimate the derivative of this at 12. Notice 12 is not in here. And show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in the context of this problem. Okay? If I want to find the derivative of this at 12, then I'm going to look at the points on either side of this and find the slope. So that would be approximately equal to this minus this over this minus this, right? Function value, these are like our y's, right? Y minus y over x minus x. So that's 67.9 minus 61.8. And those are degrees Fahrenheit, right, that I'm subtracting there, over 15 minus 9, and those are minutes. So let's see, what does that give us? 6.1 over 6. Let me just make sure. Yeah, that's 6.1. So it is 6.1. 6.1 over 6, which gives you 1.017. 1.017 degrees Fahrenheit per minute. All right, those are the units. The units just come right out of the slope. And interpret the meaning of your answer in the context of the problem. So I'm going to say this is the average rate of change from t equals 9 to t equals 15, right? Or you could say, which is approximately equal to the rate that the water is warming at time 12. So I think either, you could probably say either one of those, and that would be okay. Part B. Use the data in the table above to evaluate this integral, and notice we have the integral of derivative, and then using the correct units, interpret the meaning of that in the context of this problem. Let's see, we want to by the fundamental theorem of calculus, if you want to evaluate a definite integral, you just need to know an antiderivative of this. And the antiderivative of this is that from 0 to 20. So that would just be the water temperature at 20 minus the water temperature at 0, which is 71 degrees minus 55 degrees, which is 16 degrees Fahrenheit. So using the correct units, it's just a good idea to keep units in these things all the time, because then the units are right there, right? I mean, I'm subtracting those things, so it's units. And this is the this is the change in temperature from T0 to T equals 20, right? It's the total amount of change. That's what taking the integral of a rate gives you. It gives you the total amount of change. Okay? So far, so good. I'm going to move on to a different sheet of paper, I think, because I'm out of room down here. So for time 0 to 20, the average temperature of the water in the tub is this. Well, we know that. That's how you find the average value of a function, right? So they told us something that they didn't really have to tell us there. Of course, the average temperature is that. 1 over how wide the interval is times the integral. Use a left Riemann sum with the 4 subintervals indicated by the data to approximate this. Okay, so to use a left Riemann sum, get that on the screen there, that means these are the heights of my rectangles, right? And these are the widths, 4, 5, 6, and 5. So if 1 over 20 times the integral, that's approximately equal to 1 over 20 times the area of the first rectangle is 4 by 55, right? It's a left-hand Riemann sum, so that's how wide it is. I use the left value for the height, plus this rectangle is 5 wide, and I use the left endpoint for the height. This rectangle is 6 wide. I use the left endpoint. And this rectangle is 5 wide, and I use the left endpoint. Let's crank that out of the calculator real quick. So I have 1 over 20 times 4 times 55 plus 5 times 57.1 plus 6 times 61.8 plus 5 times 67.9. And this is the average temperature, so we better get something reasonable, right? So that's equal to 60.79 degrees Fahrenheit. It's the average temperature, so units are temperature. Okay, so they want to know, does this approximation overestimate or underestimate the average temperature of the water over those 20 minutes, and explain? Well, I think the best explanation is, or the way of thinking about it, is like a graph. The temperature is going up. The water is being heated. They told us that. So whatever the water is doing, it's getting warmer, right? And if you find the area from here to here, and you divide it into 4 subintervals, and you use the left endpoints, then you're always going to be underestimating, right? So this approximation is low because the function is increasing, and that means W, the water temperature at the left endpoint, is always less than the water temperature at the right endpoint. Right? If we took right endpoint ones, likewise, we'd know it would be too big. Midpoint, then it would depend more on concavity. That would be it would be hard to tell. Okay. So next part D, for 20 to 25, that's not on the table. The function W that models the water temperature has first derivative given by this. Based on the model, what's the temperature of the water at time 25? Well, I know that if I take the integral from 20 to 25 of this rate that they gave me, which is 0.4 square root of t cosine of 0.06 t dt, that's the derivative, right? So just like we did in part B, I think, just like we did in part B, this is equal to the water temperature at 25, because this is W prime, right? So the antiderivative would be the actual temperature of the water, minus W20. This is just like a fundamental theorem of calculus problem, right? It's just that they're giving us the rate in a context here, so we need to think about that. And I know what the temperature is at 20, right? It's 71 degrees, right? So that means the water temperature at 25 is equal to this integral plus 71. Right? Add that to the other side. So I just need to find that and add 71 to it. So let's see. We want to do math 9 fn int. What is the crazy function? It's 0.4 times the square root of x times the cosine of 0.06x, right, comma x, comma 20, comma 25. And then we want to take that and add 71. So 80.479 degrees. 80.479 degrees Fahrenheit. All right. And let me just make sure that I was in fact in, I was in, scratch that, I was in degree mode. Somebody's been doing physics with my calculator. So let's try that again. Let me go back and get that entry back, and so 73.043. 73.043. That makes more sense. Degrees Fahrenheit. All right, there you go.